Well, good evening, everybody, and welcome to the next to last lecture for Physics in Everyday Life and Conceptual Physics, and hopefully the next to last lecture that I will have to record from the corner of my basement. Man, the 80s were weird, weren't they? And I was alive during that time. Um, Hope you are all doing well out there as you're winding down your semester. We've got these two lectures left, and then we have our final exam next week, and check your email for details about that final exam and when it will be available to you. So today we want to talk about nuclear power. Last time we talked about nuclear weapons, and in fact the mechanism behind both of them is pretty much the same thing. You just have a different aim, obviously, with both of those devices. Last time we talked a little bit about the difference between nuclear fusion and fission. Fusion, the process of joining together multiple nuclei to create a new, larger nucleus. Fission, the process of splitting apart nuclei. Now, fission happens on its own in many radioactive elements, but you can also help it by hitting the nucleus with something like a neutron. When you have something that is radioactive, it is often characterized by something called half-life, the amount of time that it takes for half of the sample to radioactively decay. And nuclear bombs, if you want to build them, require you to have a device that allows for a chain reaction, that is, one nucleus splitting, causing other nuclei to split, causing other nuclei to split, and keep growing exponentially that way. You also need something called critical mass. You need enough fissionable nuclei packed in a small enough space that in doing so you'll get the chain reaction and you'll release tremendous amounts of energy. So, as promised last time, we introduced the concept of radioactive decay and left solving a quantitative problem on that until today's lecture. So this is the problem. It deals with the potassium in a banana, a small amount of which is radioactive, and asks you to figure out how much of it is still radioactive or still undecayed, I suppose, after 1 year, and how long would you need to wait for something that has a half-life of 1.26 billion years until 99% of it was decayed. So if you have the equation for half-life from the previous lecture or from the Bloomfield text, you can actually go ahead and solve these. If you would rather see me solve them, the link to the YouTube video is down there in the corner of this slide. So I don't know where everybody's conception of nuclear power plants comes from. I suppose it depends on some level as to whether or not you live anywhere near a nuclear power plant. Maybe many of us got our indoctrination into nuclear power plants through watching The Simpsons, where Homer is employed at Springfield's nuclear power plant. But there are, in fact, nuclear power plants closer to you. Here in Iowa, we only actually have one nuclear power plant. It's the Duane Arnold Energy Center down. It's a little northwest of Cedar Rapids, down in that part of the state. And it was built, I believe, in 1975, something like that. It was supposed to be recommissioned for a number of years out since now, I think 2034, something along that line. But a couple of years ago, actually, it was decided that that nuclear plant would be shut down at the end, toward the end of this year. And I haven't seen the latest news as to whether it's actually shut down now or that's still happening later to come this year. Broad reason for it is we have much cheaper energy from both coal and wind here in Iowa. And so Alliant Energy, which had a majority stake in buying the power generated by this atomic reactor in Iowa, has decided to not purchase more power, and so they are going to actually shut this thing down. But you can see from the map there, this is, I believe, Region 3 of the U.S. nuclear power plants, and there are several in the Midwest. Importantly, they're all near bodies of water or sources of water, and there are many more throughout the country, though we are certainly not by any means the most nuclear-powered nation on Earth. And, you know, ever since nuclear power plants came into existence, they've been a subject of some contentious debate. So we're not here to settle that debate or make you decide on one side or the other of the nuclear issue, but rather to talk a little bit about how a nuclear power plant works and what are the disadvantages and advantages of nuclear as a source of energy. So nuclear power plants are arguably not incredibly complex devices. You have to have something that is producing energy through a nuclear reaction, and so that's the core part of the nuclear reactor here. And there are something called control rods, which we'll talk a little bit more about shortly. They're all contained in a pressure vessel. Typically, the container that contains this core is also filled with a large amount of water. And then there is a path that circulates this water that is in the core. And this is a closed system here. So you'll notice on this particular artist diagram, hot water is going to flow through here and then return back to the reactor via the water pump. And so the water in this part of the path actually doesn't interact with any of the other parts of the system and does not interact with the water in the nearby water supply, which is used for cooling this device. So this one path of water heats another set of water, and it's this set of water that if you boil it, produces steam, and the steam is fed generally quite a ways away from the nuclear reactor part of the plant to other buildings which contain one or more steam turbines. And then just like the old steam engines from the boats on the Mississippi River in the days gone by, this turbine is turned from that steam. This turns an electric generator, and we've talked about the physics of that in previous lectures, and that produces electric power that can be fed out via transmission lines into the power grid. That water, that steam rather, can then be recondensed into water and recycled throughout this system. And so really what you need for a nuclear power plant, since it produces a tremendous amount of heat, is you need a source of cooling. And water, having a really high specific heat capacity, is a good coolant. And so most often you see these nuclear power plants built somewhere where they have access to a large body of water. And again, the water that they're pulling in from a river or ocean or lake or whatever is used as the cooling source is not coming into any direct contact with the nuclear materials that are in the nuclear reactor, but rather it's just used as a cooling apparatus. And so if you are near a nuclear power plant and you see those famous sort of shaped, funnel chimney things, if you will, that are releasing large clouds, that's all water vapor that is being vaporized within the cooling cycle. It is not nuclear material. It is not radioactive. So in that core, there are fuel rods, and the fuel is most often made out of uranium. If you recall from last time, uranium-235 is the radioactive isotope of uranium. But then, because our goal is not to have a bomb and not to have a critical mass with a whole bunch of uranium packed close together, there's other materials called moderators that are used in between control rods. Sometimes they're made of graphite, sometimes other materials, but they are materials that actually act to slow down the neutrons that are emitted when uranium-235 fissions and splits apart. And then you have other devices that actually absorb neutrons, and they make a series of control rods. And so the position of these control rods relative to the fuel source can be used to speed up or slow down a reaction and keep it within a range that you would like to keep it within. You don't want your nuclear plant to melt down, you don't want to have a bomb, but you also don't want to have the reaction go so slowly that you're not generating a usable amount of energy. So the FET simulation that we looked at last time with nuclear fission actually has a third tab, and it is a simulation of a nuclear reactor. If you want to play around with it, the simulator is linked up there on the link in the top of the slide. Again, it is an older Java-based simulation, so you have to be able to work around that on your computer. But it's not going to play my movie. Let's go back here and see if we can... I went ahead and just played around with this reactor. And so here you actually have an adjuster for control rods, and then you have a device that fires neutrons. So right now my control rods are in between my fuel cells there in the reactor, and when I fire neutrons, I may get a few of these uranium atoms to fission, but they don't trigger any sort of other chain reaction here. It's only when I actually have those control rods removed from their shielding that I get a whole bunch of fission events to trigger other fission events. And you'll notice that drives the power output higher and also drives the energy produced higher in this setup. Now, it might be that I don't want to produce power at that rate, like this is going to make my reactor too hot, or I don't need to generate this much electricity at the time. And so you can actually adjust the position of these control rods within the core of the nuclear reactor and slow down the reaction. So I believe here coming up, I raised the control rods. Well, this is full bore. I guess I was trying to see if I could blow up the nuclear power plant in the simulator. I'm not sure that you can. But if you actually do it with control rods partially in place, you'll notice that even though you get triggering from one fuel core to another, your reaction does not go as quickly, and so you get a lower amount of power reduced. If you put all those control rods in place, you really kind of shut down the reaction that's happening there. All right, so the first of 3 Poll Everywhere survey questions for this lecture. What is it that turns the turbine in a nuclear power plant? Is it electric current? Is it uranium? Is it water? Is it wind? So Bloomfield in the book talks about the workings of a nuclear reactor, and I could talk about the basics of that, and in fact I did a couple of slides ago. But I think it's actually really illustrative to look and see an actual nuclear reactor. And there are people that have done a better job for this because they actually have an available nuclear reactor. When I was studying engineering out in Washington State, we toured a shutdown reactor at Hannaford, which is in the Tri-Cities area of Washington State. And I remember it was quite an interesting experience, you know, kind of mind blown for an early engineering student to see a huge thing that had some precision engineering elements to it. But I've included here a couple of YouTube videos. You certainly don't need to watch both of them unless you have an interest in doing so. But I would like you to watch one of them just to get an overview of how a nuclear power plant is set up and how it functions. You know, what do the actual things look like rather than the artist's rendition there. So the first I found was a walkthrough actually of a power plant near Toronto, Canada. This is the Darlington Nuclear Power Plant. And it goes through and gives you the basics of how nuclear power is generated and then how that's converted into electric power. It is in truth sometimes feeling like a corporate video where there's, you know, little bits about safety and worker training and things. And so you're more than welcome to watch those, but you'd be welcome to skip through those as well. It's basically the first part of the video and then towards the end of the video that they give you the meat of how the system works there. On the more academic side, if you're interested, MIT has what they describe at least as the second largest research nuclear reactor on the campus there in Cambridge, Massachusetts, outside of Boston. And so the video on the right is a walkthrough tour of that system. Now that's a reactor, and the reactors on college campuses usually are to do experiments and nuclear testing and things of that nature with, not to generate electricity, and the MIT one is an example of this. So there's a lot of research work that happens in conjunction with this. The core of that nuclear reactor is exactly the same as the core of a reactor for a commercial power plant. They're just not using it to generate electricity in there. But nonetheless, it shows more actually of the active reactor in the video on the right than it does on the one on the left. So I would like you to watch one of those or YouTube on your own and find a walkthrough video of a nuclear power plant. There seem to be half a dozen or more of them out there. All right. So if you watched the video or were paying attention 3 or 4 slides ago, you should know the answer to this next Poll Everywhere survey question. What fuel do they use in the core of a nuclear reactor? Gasoline, silicon, uranium, or water? And the final Poll Everywhere question of this lecture, both of the videos, if you watched one or the other, you should have seen this, show workers actually when they're done going around in the plant, placing both of their hands into a machine that checks them for radiation. They wait a short period of time, and then there's a message on the screen. What does that message say? Does it say all clear, clean, normal, or safe? So, nuclear power, like almost every form of power, has pros and power production, rather, has pros and cons. People that think this is the greatest thing ever people think this is the worst thing ever, and some of the rest of us who are probably somewhere in the middle of that spectrum and can see that there's good and there's bad in almost any way that we choose as humans to generate electrical power. So, one of the pros of nuclear power is it's a pretty efficient source of energy. The energy that you can get out of 1 kilogram of uranium gives you the same amount of energy as burning 20,000 kilograms of coal. So it is a densely packed source of energy. Even as the book points out, you don't need highly refined uranium like they had to have in order to make the atomic bombs we talked about last time. In this age of climate change uncertainty, it does not actually emit appreciable amounts of carbon dioxide in the production of electricity via a nuclear reactor. Most of the stuff you see rising out of there is steam from water that has been heated and is part of the cooling process. So it doesn't emit carbon dioxide and contribute to the greenhouse gas issue. It is relatively inexpensive once you have it up and running. You need a staff to run it there, but you don't have the fuel demands that you have at, say, a coal power plant or something of that nature. And once it's up and running, again, it's a pretty cheap source of energy for producing electricity. It's also not weather dependent because there are, Iowa famously is a very wind powered state these days. I think I saw a headline in the Register just a few weeks ago that wind has now surpassed coal and become our number one source of energy production in the state of Iowa. Wind's great. Wind is not without some drawbacks of its own, but one of the drawbacks of wind is if the wind's not blowing, you don't get this, right? Solar, if the sun's not out, you're not producing solar energy. Nuclear energy can be produced at any time. However, on the drawback side, it is not sustainable. It is one of these materials we find in Earth's crust. But once you've used the radioactive uranium-235 and it decays into other things, it doesn't go back to being uranium-235. And so eventually we will probably run out of uranium to mine, just like we'll run out of fossil fuels to dig out of the ground. And so it is not a sustainable energy source as far as we know. It also, as you're probably aware, produces radioactive waste. So yes, uranium-235 decays in the production here, but you don't get all of the uranium-235 to decay. And so those cores, once they're done being useful in the nuclear power reactor, are still radioactive, and other materials that are used in close proximity are radioactive, and we don't have a great way of dealing with them. They seal them in containers and store them because these are radioactive for thousands and thousands of years. And so I can remember periodic news stories throughout my life where, we've decided that we're going to build a storage place for the nuclear waste in some mountain range in Nevada. And then, people from Nevada are up in arms about that. And, there's no good place to store this stuff often, and that becomes a problem. While it's cheap to run and operate once you have it, there are obviously millions and millions of dollars that go into the engineering and construction of nuclear power plants. And so it can have a significant upfront cost. It costs far more to build a nuclear power plant than it does to put a dozen wind turbines on your property. And you probably are aware of this, but there are occasional failures for nuclear systems. And they're pretty rare. Bloomfield talks about 5. There are a big 3 in my mind, but there have been periodic problems with nuclear systems. And because the reaction at the core produces a tremendous amount of heat, which is ultimately why it's a great energy source for producing electrical energy, when things go wrong, they typically go very wrong. So the big ones, at least that I remember in my lifetime, I was a little kid when this happened, but 3 Mile Island, which is near Harrisburg, Pennsylvania, had a nuclear reactor. And it had a cooling problem in March of 1979. And so there was a good deal of radiation released during that cooling problem. That was not nearly as dramatic as Chernobyl, which was at the time, the Soviet Union, now near Pripyat in Ukraine. This was in 1986, and there was a significant meltdown event in the core of the reactor there and released a tremendous amount of radiation. And even today, now, decades later, there are still elevated levels of radioactivity in the area all around Chernobyl. I haven't seen it, but I hear that there is, in fact, a recent HBO show out about Chernobyl as well. And finally, one that you may remember in your lifetime, in 2011, the Fukushima nuclear power plant in Japan had another meltdown event. And actually, you can see that picture was grabbed while it was in progress. And there's other pictures you can find of the same thing, of barges there, shooting water on, trying to put this fire out in this massive meltdown event. So there have been obviously big disasters, and they have serious consequences in terms of the health of people around there. But, like anything else, I think you'd have to consider that versus accidents and problems that are inherent with any other form of energy production. It's not free to extract oil from the sea, for example, or dig coal from the ground, and things happen in all of those situations. So that's all we wanted to talk about today, and one more lecture here to go. We talked a little bit about how nuclear fission, which we introduced last time, can be used to generate electric power in an electric power plant. Basically, the fission creates heat. That heat gets captured by water. That water typically heats other water that are disconnected from each other so that you don't have radioactive water moving through most of the rest of your nuclear system. You produce steam eventually. That steam can turn a turbine, and that turbine turns a generator, and that produces electrical energy that's transmitted out over transmission lines. Uranium-235 is the fuel source in most nuclear reactors that I'm aware of. But even though much of the uranium-235 is quote-unquote spent after being used in the core of a nuclear reactor, there's some amount of it that's still radioactive. And that fuel and associated materials have to go somewhere that they don't pose a health risk to people. And so this is one of the contentious debates about nuclear power generation. Where do you store the waste that's produced in doing this? And like most of our means of producing electricity, nuclear power has key advantages and disadvantages. It has a generally safe track record, but it has some very notorious meltdowns where it was not safe. And that certainly has influenced public opinion and the folks that are opposed to using nuclear power as part of our energy landscape. The discussion today goes along with section 15.2 in the Bloomfield text, and you are almost done if you've read that section. If you want to take a look at the recommended problems for chapter 15, they should be up on Blackboard. And the very last section, the one we'll talk about in Friday's lecture on 15.3, deals with medical imaging, something that might be much nearer to your experience if you've ever had an X-ray or an MRI or something like that, even if you've never, been in a nuclear power plant or a nuclear war. All right, hope everybody's having a good evening out there. Stay safe and check email for the announcement about the final exam that will be coming out here shortly.